Hello again. We're going to launch into a little more acid base here in the second lesson. A couple of things to tell you. Most of these equations, if not all of them and probably more, are on your equation sheet. I believe I mentioned that in class. You don't have to memorize any of these. The AP does write the equation for KW this way. Okay, so I've been kind of hedging and saying, oh, I'm going to use H3O plus and H plus. I suppose I should just switch over and say we're just going to use the H plus because that's what you're going to see on the equation sheet. But that's on the equation sheet. This is. There's an equation about pH and pOH for all solutions. So please familiarize yourself with those. These apply to all aqueous solutions, whether or not they have an acid or base in them. It is important that we talk about why some species are acids in water, okay? And this really has to do with the structure of the particle and the polarity of the HO bond. Consider a molecule such as HCl. This is clearly a polar molecule. It's a polar molecule in which the electrons are drawn in the direction of the Cl, making that a delta minus and this a delta plus. Now, if the HCl were simply isolated on its own, it would stay HCl. But what if there's a polar water molecule nearby? Okay, in that case, this hydrogen may simply move over and form a bond next to the unshared pair of electrons on oxygen, because in that case, it might actually have a better share of that electron pair than it does in the HCl bond. And so what would happen is there is a transfer of the H plus or proton from the HCl to the water molecule. Okay, this is the behavior that we would consider acidic behavior for the HCl if water is nearby. If water isn't nearby, clearly this isn't going to be able to happen. Okay, so there's a structural thing going on here. If the hydrogen in the original acid that we had over here is feeling its electrons pulled away from it rather strongly in water, it has a tendency to say, fine, adios, chloride, take my pair, I'm going to go hang out with the water molecule. Now, this does not mean that all of the hydrogens in an acid behave as acidic hydrogens and do the behavior that I described on the previous page. This is the structure of the acetic acid molecule, and you'll notice while it has 4 hydrogens in its structure, only one of those hydrogens will have any tendency to be acidic, and that is this one. And that's because it is in a polar situation, bonded to oxygen, whereas the other hydrogens are bonded to carbon, and there's very little electron shifting in a carbon-hydrogen bond. The same would be true of benzoic acid. There are plenty of hydrogens in benzoic acid, and yet it is only this one that is acidic in this structure. So take a look at H3PO3. You, I think, will notice that it is diprotic. It can ionize this hydrogen and this one, but the polarity of this bond is not as significant, and therefore that one is not acidic. So this would be called a diprotic acid. It would be able to ionize 2 H plus ions. This is a lovely diagram from your textbook about various oxyacids in which the HO is connected to some other atom. In this case, we're looking at the halogens, okay? And you notice that as the electronegativity of the halogen increases, the strength of the acid also increases, okay? And that's because of an electron shift, a more polar bond, and then an easier transition of the hydrogen from the original acid molecule to the water. please do pause and sort of read through this and try to orient your brain on what's going on here. So here is a similar situation, kind of related. Okay, in this case, I have a Cl and an O and an H, and we're talking about the hydrogen being the acidic particle that is going to leave the molecule. But if you look at the Ka values are increasing as I build up more cumulative electronegativity by a greater O population attached to the Cl. So in this case, I'm looking kind of at a cumulative electronegativity that takes this bond here between the hydrogen and the oxygen and weakens it further, making it easier for the H plus to disconnect from the molecule. Polyprotic acids, much like the one that 2 slides ago I called diprotic, have more than one H plus or proton that they can ionize, and in solution they ionize in steps. So let's look at this first example here. Sulfuric acid has 2 ionizable hydrogens. That is a result of this Lewis structure. And you'll see that the first step is actually 100%. This first step represents a strong acid, and the second step is an equilibrium step. So this molecule H2SO4 releases all of its first hydrogen and then only some of its second. The same sort of thing happens with this acid here, carbonic acid. Now, if we consider subsequent steps, for instance, a first ionization and a second ionization, okay, the Ka of the second ionization is always less than the Ka of the first ionization. Okay, it is less likely for subsequent hydrogens to be ionized. Some of that stems from the fact that the conjugate base of the original acid has a negative charge, making it less likely for that second hydrogen to leave that negatively charged particles. Okay, so the Ka of the first ionization is always greater than that of the second, and if there's a third, the Ka of the third ionization is less than that of the second. So next we're going to talk about determining the pH of an acidic or basic solution. And our first example is strong acid pH. I'm going to teach you guys about strong acid and strong base pH first, then we'll deal with weak acids and bases in a subsequent lesson. So HNO3 is a strong acid, which means that it ionizes 100% in solution into H plus and NO3 minus. Now, I guess I could look at this as an ice table and say that I started out with 0.2 molar and none of those, okay? But it doesn't really make sense to use an ice table because this isn't an equilibrium. What happens is all of my acid ionizes, and so I will push my entire molarity to the products. And this will be gone once that solution has a chance to ionize. That means that in order to find my pH of this solution, I'm going to take the negative log of the H plus, which is equal to the negative log of 0.2, which equals 0.7. So I have a pH of this solution of 0.7. This is true for all strong acids of any concentration. Whatever the original molarity of the acid is converted entirely to H plus. Okay, so it's a pretty simple calculation. Strong bases, also fairly easy, but let's talk first about how to identify a strong base. Okay, a strong base is a short list. There are very few. They are group 1 and group 2 at the bottom hydroxide compounds. So, NaOH, KOH, LiOH, etc. And barium hydroxide is a strong base. I'm not looking at my periodic table here. Strontium hydroxide is a strong base as well. Calcium's borderline. Calcium, I'm going to say no. Okay? So, how do we find the pH of a strong base? I would suggest we do the same thing we did with the strong acid, which is write what this stuff does when I put it in water. KOH put in water will fully ionize into K plus and OH minus. And that means that if this were 0.2 molar originally, it will completely be gone, and the concentration of the K ion and the hydroxide ion will both be 0.2 molar. So it's very similar to what's happening for a strong acid on the previous page. However, this is not an H plus concentration. However, if I take the negative log of the concentration of OH, that gets me the POH, and pH plus POH equals 14, so I can subtract from 14 to find the pH of my solution is 13.3. Okay, so an extra step here. Same kind of thing would happen if I had barium hydroxide. The difference here, however, is this ionizes and provides 2OH. This is essentially an ionic compound, so it's just going to ionize into positive and negative pieces. Okay, and in that case, my concentration of OH is going to actually equal 0.4 molar, and so I will find POH and pH, which will be equal to 13.6. I hope that makes sense to you, that the pH here is higher because I have more OH present in the solution than I did for the KOH example above. So that pretty much takes care of strong acid and strong base pH. We will do some more examples in class. Note some questions and bring them to class if necessary when I see you next. Thanks, guys. Have a good one.